Nature has become a source of inspiration for many disciplines of life. Think, for example, Monet's paintings, using pigs for heart valves, and even robotics. It's one of our best sources for new ideas. When engineers use nature to influence their designs, we call this biomimetics. This has led to numerous innovations in robot design. So, what have engineers taken their latest inspiration from? That's right. Mountain goats. They are some of the most balanced animals on the planet, seemingly defying gravity at times. So, what does this mean for robotics? Researchers have looked into why goats are so balanced, hoping to apply the same mechanical principles to their own quadruped robots, like the one shown here. The goal is to make the robots more stable and therefore capable of walking on uneven terrains. To do this, we must answer the question, why are mountain goats so balanced? Their balance can be attributed to their specialized anatomy and specialized biomechanics. After measuring things like body positioning, joint anatomy, and force generation, researchers have found three main features that contribute to the goat's impeccable balance. These include optimal centers of mass, controller force generation of their limbs, and specialized hoof joints. Let's start with its center of mass. For context, every object has a center of mass that by definition, is where you can assume all mass is concentrated. You can think of it as a balance point. For this ruler, it has an even weight distribution, so its center of mass is right in the center. For this hammer, since the head is much heavier than the handle, its center of mass is closer to the side where a majority of the weight is distributed. Now let's look at the goat. For the goat, a majority of its weight is located close to the ground and towards the front half of their body, which is also called the cranial direction. This is very helpful, particularly when going uphill. The closer the center of mass is to the surface, the less likely the goat is to tip backwards. Compare that to a human, our center of mass is much higher, and therefore further from the mountainside. This makes it a lot easier for us to tip and fall, so that marks the first feature in goats that aid in their stability. Now let us talk about force generation. When walking, goats generate propulsive forces from their forelimbs and hind limbs to propel them forward. The amount of force generated by the forelimbs and the hind limbs changes based on the incline they are walking on. On a positive slope, both generate force, with the hind limbs providing most of the power. When walking downhill, this changes. Now, the goat needs a way to stop itself from tumbling forward. To do that, they stop generating propulsive force with their forelimbs and instead turn them into brakes, while the hind limbs deliver the necessary force to continue forward movement. So how do we apply this to robotics? Researchers can use these concepts in their existed quadruped robots, particularly in the design of their control system. Controls are very complex and often one of the most difficult steps in creating working robots. Let's simplify things a bit. Think of a controller like the brain of the robot. It takes in information from sensors like speed, positioning, and force. The controller then sends commands to the robot to tell it how to adjust to achieve whatever positioning we want. Just like how if we want to move, our brain will send signals to activate our muscles. A robot's equivalent to a muscle is something called an actuator. This could be something like a motor. When developing a control system, by understanding the principles that maintain goat balance, roboticists can tell the controller to send signals to maintain certain positioning to mimic this. So we would want our controller to do the following. Adjust the body positioning of the robot to maintain a slightly forward center of mass when going uphill. Properly distribute forces to the forelimbs and hind limbs based on terrain. This would mean signaling a majority of the force to the hind limbs when going uphill, and almost none to the forelimbs when going downhill. Robotic control is not the only thing influenced by goat biomechanics. The actual anatomical structures of goats have also found their way into robots. Now that we've covered the first two features, we can now discuss goats' specialized hoof joints. Researchers have found that goats have three main joints that control hoof movement. These are the coffin, fetlock, and pastern. The coffin joint helps move the hoof up and down. The fetlock joint allows the hoof to rotate, think rolling your ankle. Finally, the pastern joint moves the hoof side to side. These joints all work together to stop the goat from slipping. Sarah Abdad of the University College London recreated a robotic hoof and experimented on it to see how flexible each of the joints should be to provide the most resistance to slipping. Another term for this is joint compliance. Her research found that the more flexible the coffin and pastern joints are, the better. This makes sense. Both of these joints allow the hoof to have maximal contact with the ground, increasing friction, therefore preventing slips. Conversely, a non-flexible fetlock joint is optimal. This also makes sense because once again, think about rolling your ankle. If your ankle wasn't able to rotate as much, you wouldn't be able to roll it and lose your balance. So if the fetlock joint has less compliance and is therefore more rigid, it cannot roll and disrupt the goat's balance. Now there is one last feature of a goat hoof that is too interesting to omit. Think of modern cars. When you hit an ice patch, the car senses this and it begins to pump the brakes. This is called the anti-lock braking system. It seems that nature figured this one out before we did. Goats use this same concept and have their own anti-lock braking system due to their coffin joint. When slipping is sensed, the goat makes micro-adjustments via their coffin joint to generate quick, controlled contact force with the ground, synonymous to pumping the brakes of a car. Abdad directly applied these principles in her work where she modeled each of the joints as springs with particular spring constants based on the joint compliances discussed earlier. For the coffin joint, because it has its own form of the anti-lock brake system, Abdad implemented a spring with an oscillatory nature to mimic the intermittent adjustments made by the joint. By doing so, Abdad created a functional robotic leg with enhanced slip resistance and thus balance. In this presentation we have learned about why goats are so balanced as well as how this can be applied to robotics. Now what will people do with this? There is a large market for walking robots, especially those with great balance and slip resistance. This is because they can be used in a variety of different settings that could be dangerous or too difficult for a human. These are things like search and rescue missions, navigating through disaster zones, or even excavations. Nature has been a source of inspiration to engineers for hundreds of years, and the content in this presentation is just a small piece in how we can use the principles of biomechanics to push the boundaries of robotics. The future of innovation is closer than you think, especially thanks to the humble mountain goat. Thank you for watching.